Today we're taking a look at qualitative properties of solution. Most chemical reactions occur in water, so it's important to understand solutions. The definition of a solution is a mixture that has a uniform composition, so you cannot see the different components of the mixture. Solutions are composed of a solute, it's the substance that is being dissolved, and a solvent, the substance that is actually used to dissolve. Typically, in our applications, the solvent will be water. When the solvent is water, we say that it is an aqueous solution. And to denote that something has been dissolved in water, again, we use the AQ symbol. There's a bunch of properties of aqueous solutions that we're going to look at today, but one of them is solubility. For something to be soluble, it's important for it to have most other properties. If it doesn't dissolve, there's very little that we can actually analyze about a solution. So making sure that you know how to use your solubility table on the back of your periodic table. We'll do that in the next slide, but a couple of things to note. Potassium and sodium ions are always soluble. So anything with those two ions will always be AQ. Same with anything containing ammonium or nitrate. Those will always be AQ. Elements, aka something from the periodic table like a metal or like hydrogen or phosphorus, any metal or element, has low solubility, meaning that they will not dissolve in water, and they will just be their own state as they appear on the periodic table. So metals, for the most part, are solid, with the exception, of course, of mercury. H2 would be a gas. P4 would be a solid as well. So they just keep their regular symbol. They do not dissolve in water. My solubility table got cut off here, but let's take a look at it and do our best. So the solubility table, anything up here is very soluble, meaning it will be AQ in water. And anything that is slightly soluble will be, for the most part, solid in water. It's slightly soluble because just a teeny tiny amount will dissolve, but not enough to be noticeable or to give any properties of that solution. So we can see here that I've written like sodium is super soluble, ammonium is super soluble, NO3 is super soluble. You can add K plus to that table as well. When we read this, we will find typically the anion or the negative ion up at the top in a compound. And then underneath, we'll look for its metal that's part of the compound and decide if it was up here, if it was aqueous, or if it's down here, that it is solid. So when we take a look, let's look at a couple of the examples on page 11 of your notes. For instance, let's look at sodium carbonate. To decide if that is soluble or not, we're going to write its formula, which is Na2CO3. So we're looking for CO3 along the top. So we find it in this column here. And it says here that these ions are soluble with these anions. So if they were mixed with hydrogen, sodium, potassium, or ammonium, they will be soluble. But pretty much everything else is insoluble. There is an exception. If we had lithium carbonate, it would be soluble. So sodium carbonate is soluble, and we would give it a state of AQ. Let's take a look at E there, copper 2 carbonate. Chloride. So copper 2 chloride is CuCl2 because we have Cu2 plus and Cl minus. So looking in the Cl minus column, we can see that there is copper, but this is copper 1 plus that is insoluble. Everything else is soluble. So because we have copper 2 plus, we don't have copper 1. It's important to note that copper 2 would fall into the most category and that this would be soluble, so AQ. So charge matters on our multivalent ions. Conductivity of a solution is related to the type of compound being dissolved. So something that is an electrolyte is a solution that conducts electricity. A non-electrolyte does not conduct electricity. Things that conduct electricity are soluble ionic compounds, and anything, again, that's ionic hydroxide that is soluble. Non-electrolytes, things that do not conduct electricity, are molecular compounds, and anything that's insoluble ionic does not dissolve. It doesn't create ions, so it can't dissolve. The diagnostic test for this is a simple conductivity meter. There's something that have two leads and a little light bulb on them. And if the light bulb lights up, it conducts. And if it does not light up, it does not conduct. We've taken a look at some of these. So again, fill those in. Sodium carbonate we did, Na2CO3. It was soluble. So if it is soluble and it's ionic, it does conduct. It is an electrolyte. Copper 2 chloride, remember, CuCl2 also is soluble. Therefore, it will conduct. Note that these will pretty much always match. If it dissolves as an ionic compound, it will conduct electricity. Litmus test. Acidic solutions will turn blue litmus red, and basic solutions will turn red litmus blue. To show that something is acidic, it has to have a hydrogen. Whoops. Anything with a hydrogen out front or a COOH at the end. So for example, H2SO4 is an acid, and CH3COOH is an acid. Basic solutions have an OH minus in their ionic formula. They have to be ionic, okay? So ionic hydroxides could be NaOH, of course, NH4, OH, CaOH2, anything with a hydroxide. Neutral solutions have no change in color of litmus paper, so they are all molecular. Or they can be ionic without an OH minus. So for instance, NaNO3, because it doesn't have an OH, it's not ionic. It's not basic, but it is ionic. Another one could be Na2SO4. Another one is CH3OH. Now this looks tricky, and it's one of my favorite examples. It's got an OH with it, so it looks like it should be basic. However, this is not an ion. Therefore, this is molecular. This was methanol. It is not basic, it is neutral. So to test litmus, of course, we're just using litmus paper. We have neutral litmus paper where you could just test one strip of paper instead of having to do red and blue. It does it all in one go. Creating a precipitate, when two solutions are mixed together, sometimes an insoluble solid or precipitate is formed. We can use this information to help identify solutions. So when we use this, we're going to use our solubility tables as well. So in this example, is a precipitate formed when the two chemicals mix? If so, what precipitate is created? So you can write the balanced chemical equation if you'd like. So Na2CO3, sodium carbonate being added to calcium chloride solutions. And we're just going to do a double replacement here. So sodium and calcium switch. And we're going to get sodium chloride and calcium carbonate. So then we would check here the solubility of both of our products to decide is a precipitate formed. Another quick way to do this, though, is I can just write out the ions. So Na plus and CO3 2 minus. And Ca2 plus and Cl1 minus. What we're going to do is we're going to check the solubility of the opposites here. So notice that NaCl was one of our products, and calcium carbonate was the other. So it's just a quick and easy way without having to write an equation to check the solubility. What you'll find is that sodium chloride is soluble. Calcium carbonate is not soluble. So precipitate is made, and it is calcium carbonate that is made as a precipitate. Try the other examples here to double check your work. Like I said, precipitates can be really helpful. We have 2 unlabeled beakers of a solution and knew that one was sodium iodate. Let's write down that formula. So Na plus and IO3 minus. And the other was potassium iodide, so K plus I minus. What solution could the student add to each beaker to correctly label them? So we don't know which one is which. We just know that one beaker has these ions and one beaker has these ions. So because I have some experience, I know and remember from our quick little solubility table that sodium does not precipitate with anything and potassium does not precipitate with anything. So I'm going to add a solution that makes a precipitate with one of these ions, but not both. Okay, so looking at my solubility table, I find that iodine, I minus, precipitates with with very little. It precipitates with copper, silver, mercury, and lead too, but it is soluble with most. However, if you look at IO3 minus, it is only soluble with a few things. The rest are insoluble. So it is insoluble with lots of things. So we just need to pick something that this is insoluble with, that doesn't fall into the copper 1 plus, silver, mercury, or lead. Okay, so I look at the list there, and IO3 minus is soluble with lithium, but so is iodine. I can't choose nickel because both things will be soluble with that, and I can't choose zinc because both things will be soluble with that. But I could, for instance, choose aluminum. Aluminum would be insoluble with this, but it will still be soluble with I minus. I can choose almost any metal with the exception of lithium, nickel, zinc, and then this list because both will be insoluble with those. So the world is your oyster, and I'm going to pick that I would always try and combine it with nitrate because nitrate is soluble with everything. So this is the compound or solution I would add, but again, you can choose almost any metal here. The color of a solution or the color of a flame that is produced when an ionic solution is burned can be used to identify ions present in that solution. Some metal ions emit a specific color when they are burned because, let's go back to Bohr. So let's look at lithium, for instance. Lithium is in the second row, so it needs 2 levels, and it's got 3 electrons total. When lithium is heated, it gains energy. This electron is allowed to gain some energy, and when it gains energy, it's allowed to go into this level, and it continues on moving around in this level until it cools off just enough that it doesn't have the required energy to stay there anymore. Remember, it's a finite amount of energy. So let's say it has to have 1,000 joules to stay here. And if it doesn't have that, if it has 999, it's falling back down to this level where it's 800 joules to stay here. What has to happen is when it falls back down to this level, it's still got some extra energy. It's got 999 joules, but it only needs 800. So what happens is it emits this energy as a wave. Okay, that wave is what we see, and that's the color we would see. Different flame colors are listed on the back of your periodic table, but there's also ion colors in aqueous solution, so be careful which table you're looking at. Let's use that right now. So the following chemicals are mixed into water and sprayed into a flame. What are the colors of the solution and the flame? So let's take a look at sodium chloride. Sodium chloride has Na plus and Cl minus ions. So the solution color and the flame color is what we're looking at here. And I put our tables in. So you can see that there's the flame color of elements and there's the solution color of elements. Unless otherwise specified, let's use this column. It just means that it's more concentrated than the column next door, okay? And so we're gonna get a more vibrant color. That's all it is. So the solution color of NaCl, we're going to look through the common aqueous ions and see if any of the Na plus or Cl minus are listed there. And I don't see sodium or chloride. So that means that the solution color is colorless. And we know this, table salt in water is a colorless solution. Then we are going to scroll through the flame color of different elements. And because we have sodium present, the flame color will be yellow. Let's try one more. Potassium permanganate is K plus and permanganate is MnO4 minus. So let's look at the solution color and the flame color. Taking a look, we can see the solution color. We don't have chromate, chromium, chromium-2, cobalt, copper, dichromate, iron, manganese. We don't have manganese itself. We have permanganate. So that is a deep purple solution color. And then looking through, we can find the flame color. Either looking for potassium, you can see that these are mostly metals, or permanganate. You can see that potassium has a violet flame color. Just be sure, again, that we are looking at the right tables here. There are two tables, one for flames and one for aqueous ions or ions in solution.